Dr. Nat here. So welcome back to chapter 15. We are still with thermal processes in gas. We are now currently at part 10. Just kidding, it's part 5. So we are at part 5. Banyak kan? I know I am tired too, but this is important for us to learn. Okay, so we already talked about isobaric, right? So isobaric, let me just write that down. Isobaric means constant pressure, right? We already talked about this. So W equals to P delta V. This equation is wrong because we forgot the minus sign. So W equals to minus P delta V gives you work done, right? And the P in this case is constant. So just plug that into your first law of thermodynamics and see what you get. So your how do I say this? Your exercises on this chapter should be done together with your respective lecturers. My job here is to revise the concepts with you, okay? And hopefully make you understand this chapter better. Okay, so moving on, we are doing adiabatic. And if you guys still remember, adiabatic means that Q is equal to 0. So what does that mean? Q is equal to 0, it means that no heat energy is absorbed or released by the gas system to the environment. So it's not absorbing, it's not releasing, there's nothing, there's no heat going on. Okay, now, does that mean your temperature is a constant? The answer to that is not necessarily. Now remember, our first law of thermodynamics states that delta U is equal to W plus Q. Even though Q is a 0, I'm just crossing that out, the change in internal energy can still come from the work done. And the change in energy can be in the form of the rise in temperature, the change in volume, or the change in pressure. So let's take a look on how that is. So we have a piston over here. This piston is filled with hot gas. So inside here, this is hot gas. So this hot gas is, when you put it in a piston, don't ask how I put it in the piston, but just assume that we have hot gas in a piston. What happens to the piston? The hot gas, you know how gases move randomly and bounces off the wall, and if they are hot, they do this more vigorously, which means that they will be pushing, the air molecules will be pushing aggressively against the walls of the container, and it would want to expand, right? It would want to expand, and the piston allows this to happen. So hot gas would want to expand and the piston allows this to happen. So we are going to move our piston down a little bit. Okay, so now our gas has expanded. This is our final state. And you're gonna ask me, Doktor, bukan ke kalau gas panas dia akan release heat to the environment? Okay, betul. But in this case, this happens in a split second. I want to say from the initial state to the final state, this happens in 0.001 second. Your brain can't even quantify that. So, sekelip mata je from the initial state to the final state, which means that it is a rapid process. It happens very, very fast. If the process is not happening fast enough, then there is a possibility that Q is released or Q is absorbed from the environment. However, when it is happening very, very fast, Q, there's not enough time for significant heat transfer to occur, and we can approximate this to Q equals to 0. So an example that is common, it's not common, but an example of an adiabatic process is the combustion of your the combustion of your car engine. So when it burns fuel, you have very, very hot gas. Yeah, it's the same thing happening here. So this is your fuel, you burn it inside here. There is hot gas. The hot gas, what does it want to do? It wants to expand. And this process happens very fast in a way that all the burning of that gas is immediately transferred as work done, which is pushing of the piston. Which means that your engine is at maximum efficiency if it is not losing energy in the form of heat, right? Okay, so that is an example of a diabatic process. Now, how does it look in a graph form? From the initial state, we know that we initially had hot gas, right? When the hot gas expanded, the system, when the hot gas expanded, your V is a positive, which means that the system is doing, let me find some space first. So the system is doing negative work. The volume expanded, and remember we had this equation, negative P delta V. If my delta V is a positive, I would have negative work done. So the system is doing negative work. And so what happens to the, okay, so if our volume increases, remember what we have a fixed mole of gas. When the volume increases, we are giving more space for it to bounce around, which means that the pressure will go down. Okay, the pressure will go down. Initially, we started with hot gas and it expanded. It was doing work on the environment. It lost energy, so we are going to say that the temperature goes down. Okay, so let's take a look at this adiabatic expansion curve. So this is the graph for an adiabatic process. So it is volume versus pressure graph. V is down here, the x-axis is the volume, and the y-axis is your pressure. Now, our initial state starts from 1 and our final state is at 2. So we are going from 1 to 2. So I can draw like this. So I'm going from 1 to 2. From 1 to 2, my volume increases. I went from V1 to V2, and from this graph, I can say that V2 is greater than V1, right? So yes, there is a positive V going on. And that was the case for our adiabatic process that we saw earlier from here. Next, what happens to our pressure? Going from 1 to 2, our pressure went down. Okay, so our assumption was correct. What about the temperature? The temperature is not quantified here, but it says that T1 goes to T2. So the temperature does not stay the same. Even though our Q is a 0, the temperature may change. Okay? The temperature may change even though our Q is a 0. Moving on to the next gas process or thermal process in gas, isovolumetric, and we've talked about this one before. It means that the gas system does not change in volume. And when you don't have any change in volume, it means that the gas system is not doing any work. The gas system is not doing any work. Okay, the gas system is not doing any work on the environment, or the environment is not doing any work on the gas system. It goes vice versa, on the environment and vice versa. Okay, so if the gas is doing work on the environment, that would be a negative W. If the environment is doing work on the gas system, that would be a positive value for the gas system. Okay, so this says, basically this definition tells us straight up that work done is equal to 0, which means that delta U is equal to Q. Okay, that it means that the change in internal energy of the gas system equals the energy transferred to the system by heat, either by absorption or by release. So the change in internal energy depends solely on Q, not on work done. I can make up a question. For example, let's make this in red. Okay, so I have 2 moles of monoatomic gas. Okay, monoatomic. This is very important because if it's a diatomic, then your equation will be different. So U is equal to 3 over 2 nRT. R is the gas constant, universal gas constant, and T is your temperature in Kelvin. Now, my gas has a temperature of, let's say it's 273 Kelvin, which means that it's at 0 degrees Celsius, right? And I want to know what is the amount of heat energy that I need to supply to this gas system in order to raise its temperature from 273 Kelvin to 400 Kelvin. So I want it to go to 400 Kelvin. And I want to know what is the Q needed. Now use this equation. We can use this equation. I want to know what is Q. I need to find what is the change in U, right? So the change in U, to change my gas system from 400K to 400 Kelvin from 273 Kelvin, this means that my delta U will be 3 over 2 nRT final minus 3 over 2 nRT initial. And I can factor 3 over 2 nR out to make this equation look like this. T final minus T initial, or delta T. Okay, what is my N? My N is 2 moles, so that is 3 over 2 times 2. Let me find some space really quickly. R is 8.31, and T final is the temperature that I want to go to, which is 400, and the initial is 273. So here I can calculate the delta U is equal to, so the answer is 3166.11 joules. So what is this equal to? This is the amount of heat that I need to change the internal energy of a gas system with a constant volume from 273 Kelvin to 400 K. Okay, remember this guy has a constant volume. This equation only applies if the volume does not change. Okay, so this is an example of isovolumetric. Alright, now we move on to the final thermal process in gas, which is isothermal process. In an isothermal process, the temperature does not change. Temperature is constant. Now remember, we talked about this. U equals to 3 over 2 nRT for a monoatomic gas. If your T does not change, which means that your U final is equal to your U initial, which means that your delta U is basically 0, right? So work done is equal to minus Q, or minus work done is equal to Q. If you are absorbing heat energy, you will be expanding, you will be increasing in volume, you will be doing work on the environment. Positive W means that positive work is done on the gas. This is done by releasing heat. Remember, if you have positive work, your volume becomes smaller. Change in volume is negative. Whereas when you have a negative W, this is equal to a positive Q. A positive Q means that heat is absorbed, and negative W is done on the gas. Negative work is done on the gas, or you can say that positive work is done on the environment. Remember, if someone gets negative, the other guy gets the positive. In this case, your gas gets the negative work done, which means that your environment is getting positive work. So positive work is done on the environment. But we want to make it standard. Let's just say heat release, positive work on the gas, heat absorbed, negative work done on the gas. Okay, so negative work done on the gas means positive change in the volume. We've talked about this in isobaric. Alright, so let's say I have a hot plate down here. You know what hot plates are? They heat up stuff, right? I don't know how to explain that in better words, but you know this if you've done chemistry and whatnot. Oh, we even used a hot plate in physics, but you didn't have any lab, so okay, tak apalah, sorry lah. So this is a beaker, and I cover this beaker with a cylinder. I would say this cylinder is made out of plastic. Okay, so dia macam tak absorb heat sangat lah. So this is a plastic cylinder, okay, that covers the beaker, and inside here is gas. Of course, we are talking about gas, so inside here is gas. Okay, so sorry for the diagram. So this plastic cylinder is free to move up and down because the edges are slippery. Konon lah. Okay, we just assume that this plastic cylinder can move up and down, which means that if I had a handle here, I could take it out. And if I wanted to close it, I could just use the handle and tolak. Alright, so I have a plastic cylinder. It covers this beaker of gas. Okay, so padam dulu, because this is bugging me, because this is terrible drawing. Okay, so we have this. So we have this. This is what we have so far. Hello. Okay, let me draw that again, even though it was a terrible drawing, but I appreciated the drawing. So this is our, let me use a different color. I think that's a good idea. Okay, sorry, break by 2 seconds. 2 seconds done. Okay, so this is your plastic cylinder. Inside is a gas. Now, when we have a hot plate, right? What does a hot plate do? Does it freeze the beaker? No, it makes it hot. So this guy is giving the gas in the beaker Q. It's giving the gas in the beaker Q. So what does it do? This guy absorbs Q. This guy absorbs the Q. Now remember, when we have a isothermal process, your W is equal to minus Q, or your minus W is equal to Q. In this case, you are having a positive Q. You are absorbing heat. Absorb heat, which means that you will be doing negative work on the gas. Negative work on the gas means positive change in the volume. Now, how do we make the positive change in the volume? The plastic cylinder has to move up to allow the gas inside this beaker to expand. When it expands, we can get the positive change in volume, which means that we are doing negative work on the gas, and this is equal to the heat absorbed by the gas in the beaker from the hot plate. So again, I'm going to recap. We had a hot plate. This hot plate supplied Q to the gas system. The gas system says, hey, why not? Let's take it. So the gas system absorbs this Q. Absorbing Q means positive Q, which means that there is going to be a negative work done on the gas. How does a negative work done on the gas look like? It looks like by expansion of volume. Expansion means bigger volume. So the gas system wants to expand when it absorbs heat. This is common, we know this. When it absorbs heat, it wants to expand. I want to be free, right? So this is minus W equals to Q. So this is an isothermal process. So for isothermal, we have a special case. We have a different equation that we need to remember.
Cake.
You want cake? Okay, kejap So W for an isothermal process, the work done on the gas is negative N RT natural log V final over V initial. Okay, so I hope this equation is covered by your lecturer in class. You have to know how to use this equation. Before we end part 5, let's do a little recap. So what have we learned so far? We learned about isobaric. Isobaric is constant pressure. P is constant. Okay, and then we also learned about adiabatic. And we know adiabatic, the Q should be equal to 0. There's no heat transfer from and to the environment. And then 3, isovolumetric. Isovolumetric, you know this is V is constant, which means that work done is 0. Okay, and then number 4, isothermal. Okay, I'm going somewhere with this, bear with me. So this guy is T equals to constant, and this means that delta U is 0 and W is equal to minus Q or vice versa. Okay, this guy becomes, what is it? Delta U is equal to W. Okay, and this guy we know is minus W equals to minus P delta V. Okay, so now I want to talk about PV diagrams. Okay, so this is in your module book. You can take a look. So PV diagram, what is a PV diagram? Basically a PV diagram, we've talked about this a little bit when we were discussing about adiabatic. So I'm gonna wrap up the PV diagram for all of these processes. So PV diagram is basically you have your x-axis as a volume, and this guy is in meter cube SI unit, and this guy is in pressure, and the SI unit for pressure is Pascal. Now, for an isobaric process, we said that the pressure is constant. So the pressure is constant and the volume can either expand or become smaller, right? So for example, the volume expands and the pressure is at 5 Pascal. So the volume expands, so it goes from state 1 to state 2, and this is how my diagram looks like. So it goes from state 1, this is V1, and I go to V2. My volume expands, right? It expands by V2 minus V1. So that is the amount of volume of expansion that's going on. And the pressure is kept constant. So this is how an isobaric curve looks like. Okay, so this is an isobaric curve. So moving on, adiabatic, we have seen an adiabatic. So let me rearrange this. So this guy is isobaric. The pressure is constant. Next one that we are going to talk about is isovolumetric. Isovolumetric means constant volume. So the curve will look like a straight line in the PV diagram. So it will look like a straight line. If my pressure goes from 5 to 10 Pascal, my curve will go from, this is the first point and this is the second point. This is the second state of my gas. So what do I do with these points? I connect them together, and this is the direction of my process. So I have a constant volume. My state starts at 5 and ends up at 10 Pascal. So state 1 to state 2 is going up. It's a straight line. This is an isovolumetric. This is how it looks like. Okay, kita dah tengok adiabatic in the previous part, so just take a look at that. And then isothermal. So an isothermal basically looks almost the same as an adiabatic, which we have seen earlier, but it falls in pressure less severely compared to adiabatic. Remember, adiabatic is a very, very fast process. It reaches one state to another state rapidly. So compared to adiabatic, isothermal is a slower process, which means that its graph, it can start at the same point, but the curve will be less, how do you say this? Dia lagi landai lah. So it is less, it falls down less rapidly compared to adiabatic. So here, this is my isothermal curve. Okay, so isothermal and adiabatic, the curve looks identical, but adiabatic is a fast process, so it will reach the final state faster than the isothermal. So it only needs a small amount of expansion to reach the state that isothermal wants to go. Okay, so isothermal has to go further and further and further to reach the same point as adiabatic. So where am I going with PV diagram? I want to introduce to you that we can actually calculate the work done using a PV diagram. So how do we do that? Calculate work done. Work done on the gas. Calculate work done on gas, or we can just say W gas. Okay, so how do we do this? How do we do this? So use your, no, I'm going to use my highlighter. Let's use, wow, this purple is nice. Let's use this purple. So for an isobaric system, right? So for an isobaric process, to calculate the work done is basically calculating the area under the curve. And for in this case, it's a square, right? So whatever value of area that you get here, that is the work done. Now the question comes, is your work done a positive or a negative? Now remember, when our work expands, when our volume expands, when we have a positive V, it means that we are doing negative work. If we have a negative change in V, it means we are doing positive work. Now let's take a look at the curve again. The curve is going from 1 to 2. It is going from V1 to V2. And going from V1 to V2 is a positive volume. It's an increase in volume. So V2 is obviously greater than V1, right? So your delta V is a positive. What does that mean? A positive delta V means that this work is doing, this gas, it's late, so I'm kind of tired. This gas is doing negative work, okay, because the gas is expanding. Now what about this guy, this dude over here called isovolumetric curve? So the curve goes from 1 to 2, it's going up like that, it's a vertical line. What's the work done? The work done is 0 because there is no area. There is no area under the curve. How do I calculate an area when there's nothing that I can calculate for? So okay, for adiabatic, the area would be this much. Over here, it's under the curve. How do you calculate under the curve? So you can divide it into several shapes, like this guy, one triangle, two triangles, so that is not a good triangle. So two triangles, so I have 1, 2, then I have a small rectangle over here and this guy over here. So if I know what the area number 1 is, area number 2, area number 3, area number 4, and I add them together, A3, A4, this is my work done for the adiabatic process. And similarly, for an isothermal, the entire area under the graph, okay, where the boundary is the x-axis, so it stops at the x-axis. It stops at the x-axis, it starts from the curve. So the whole area under this isothermal curve is your work done. Okay, for example purposes, let's say our adiabatic is moving from, so let's say our adiabatic is from 1 to 2. So this is how our curve goes. It's going this way. And our isothermal is going the opposite way. Contoh. Okay, so for our adiabatic, I'm using the same color. Let's use a different color. So adiabatic, the volume is expanding. Volume expanding means positive V. This means it is doing negative work. The adiabatic process is doing negative work. And if I have an isothermal and let's say that the curve is going this way, okay? So this way means negative delta V. Negative delta V means positive work. So that is how you calculate for the area under the curve to find out what is the work done by the gas process. And on top of calculating the area, you have to decide whether the work done is positive or negative. And you can do that by looking at whether this is an expansion or whether this is a compression. If expansion, negative work done. If compression or it becomes smaller, this is positive work done. Alright, so this is the end of hopefully the last part. Alright, so I'll see you. Bye-bye. Okay, so I'll see you in the last part of chapter 15. Bye-bye.